I'm trying to do.
Yeah, we didn't have.
You're so excited. No, I'm trying to go to meet. My mom didn't like that.
Okay, I do want to kind of walk through these problems. I know you guys did it for homework, but these are going to be topics that we're going to these are topics that we're going to see on the test. So let me run through these steps. So number 7, we talked about how if we see a trig problem that is too complicated for one rule to handle, we know we have to rely on U substitution. So our U value is potentially this 3 over x. There's 2 U values here because it fits into that secant U, tangent U rule. And we know secant U, tangent U, antiderivative turns out to be secant because we know our derivative, our antiderivative is just working backwards, starting on the right side of the derivative rules and moving to the left. So for number 7, we target that 3 over x as our U value. And if we want to find the derivative, we know that the best way to do that is we can avoid quotient rule by going through power rule. So we can bring that x up to the top, make it 3x to the -1. And then once we find the derivative, we can then clean it up. But 3x to -1, derivative is -3x to the -2. Now, we do want to cross multiply, but I think it's a little bit cleaner if we resolve that negative exponent and then cross multiply and then solve for dx. I think that feels a little bit less messy that way. Right, cross multiply. Trying to get dx by itself. Now that you have dx resolved, put things back into your integral notation. Remember, you're only replacing what you've underlined. Everything else, you want to make sure you keep back into your problem. So 2 over x squared, secant of u, tangent of u, and then x squared du over -3. The x squared cancels out. That is a checkpoint in terms of making sure that we're on the right track. We do need the x's to go away. And because the x's go away, we know we can move forward. The -2/3, I'm going to push out as a coefficient. And now we have a nice clean rule that we can actually identify. We know secant tangent turns into secant. So once we find the antiderivative, we can bring back our x variable. Yeah, with all these integral problems, it's always that first step. If you can figure out what that first step is, everything else kind of falls into place. But I think that's the most challenging part. Trying to figure out what that first step looks like. Okay, number 8. Evaluate the definite integral of 5x root 2 minus x dx. I do want to point out certain things to look for, especially when you're dealing with a definite or indefinite integral problem, and it could potentially be a U substitution. I meant to go over this with you yesterday or the day before, or last week, but I just want to show you that power rule problems have a certain look to it, and we need to be able to recognize, certain problems that are power rule related, even though we may assume that because we see parentheses that we're going to be using U substitution. So I just want to kind of show you 3 variations of problems that are meant to be power rule. So one is something like this. If I had x squared times x minus 1 squared over 5 root x dx. Okay. I know we see a set of parentheses, and it feels like it's a little bit complicated with a fraction, but if you look, this is manageable, right? X minus 1 squared, you can FOIL this out. You can expand this, you can distribute it. There's only one term below. Just like on the quiz, you can separate into individual fractions, then bring all the variables up, and then go through power rule. Okay. So the key component here is this exponent is not too difficult to manage, and there's only one term in the denominator. It looks like potentially U substitution, but you're going to get stuck with U substitution. This is meant to be a power rule problem. Another example, maybe something like this. Sometimes we look at a square root and we feel like, oh, maybe we have to, maybe it's difficult with order of operations. But if there's only one term inside a square root, if there's no plus or minus, then we can work with this. Okay, and again, x squared minus 4 squared. This is manageable. We can expand this out. Okay, there's not going to be any issues with that. So notice there's no plus or minus inside the square root. Let's see. Another variation that came to mind. Yeah, I think these are the 2 big ones here where just careful if you see parentheses, if you feel like obviously if the exponent is too large, then if it's more than 2, then power rule is out. If there's terms inside the square root like root x plus 1, then you know that power rule is out. But if there's only one term in the denominator or the powers is manageable, we can move forward with power rule and not have to rely on U substitution. So looking at number 8, we should always consider, can we expand our way out? There's too many terms inside the radical. We can't distribute that through. So we're stuck having to look at our second option, which is U substitution. So first things first, we want to rewrite identify our U value and our dx. We know those are the 2 things we're going to focus on replacing. So our U value is 2 minus x. Du over dx equals -1. Dx equals negative du. And cross multiply, then move that -1 over. We make our first set of substitutions here. 5x stays. U replaces the parentheses to the 1/2. times -1 du. All right, careful with what happens next. This is what some students do. They look at this and they feel, okay, I'll do power rule here, I'll do power rule here, and then do a plus C, and I'm done. Or some students would pull the 5x out and do power rule for u to the 1/2 and leave that x in the answer. So we have to recognize that there's something that's preventing us from moving forward. Okay, we cannot do our calculus process until the x's have been moved out or have been replaced. So this is a change of variable problem where the x has to be replaced in terms of u. We have to find a creative way to get that x to be moved or to be changed out. And the key here is this assigned expression between u and x. Okay, this is our relationship between u and x. We can solve for x and replace the x in terms of u. Okay. So this is yeah, put a star next to this. These are the types of problems that I think students tend to have more trouble with on the test, being able to recognize this additional step that needs to be taken. So if I solve for x here, x is equal to 2 minus u. So this is going to replace this. So we have to do some additional algebraic steps before we're ready to move forward with our calculus step, with our power rule. So if I solve for x, I get 2 minus u. Put the 2 minus u in for that x. And then there's still some algebraic steps awaiting our awaiting us to clean up, but at least we now have a path towards getting to where we need to go with power rule. Okay, so we do know that we can't do power rule until, well, first off, recognize that this is a good step, right? We've rid ourselves of x. We have everything in terms of u, but we do have to get rid of all the parentheses to get all the u values separated so that we can do power rule. But I see a lot of singular terms here, so I'm going to just move the 5, the u, and the -1 in front, and just have it as one term, and then I can just distribute just one time, rather than distribute the 5 through, and then the u through, and then the -1 through. It just feels like some additional steps that I can avoid. So I'm going to just hold the -5 and the u to the 1/2 in front. And to me, that feels a little bit cleaner because then I can just treat this like one term and just distribute through. And once I distribute through, I should be ready for power rule. So multiply this out, distribute the -5u to the 1/2 through. I get -10u to the 1/2 plus 5u to the 3/2 du. All right, so now we're ready. Now ready for power rule. Add 1 to the exponent, divided by a new exponent. 1/2 becomes 3/2 over 3/2. 3/2 becomes 5/2 over 5/2. And don't forget, when you clean up your answer, bring back your x variable. Remember, your u variable is only a temporary variable. It shouldn't be in your final answer. We should be able to represent our solution in terms of x. So once we add 1 to the exponent and divide it by it, we can flip those fractions up, multiply your coefficients, and then replace your u back in terms of x. Number 9, look at the denominator there. There's only one term. This is meant to be a power rule problem. So I did this a little differently. I brought that x in -1/2 up, but I think it's maybe a little bit cleaner to separate it. Then bring the fractions up by subtracting exponents. And then power rule your way through. No need for u substitution. There's no plus c here because we have bounds. And we can plug in the 4 and the 9. If you leave your answer in this form, that's fine. AP exam will accept this solution as well. But I just want to show you that, let's say this was multiple choice. You may be expected to get it all the way down to a number. So I do want to point out something like this, like 9 to the 3/2. This is without a calculator here. 9 raised to the third power, and then take the square root. That feels like a lot to do. What can we do without a calculator so that this process will feel easier? Instead of 9 cubed, what do we do first? Take the square roots, right? So if I can get that, now that 3/2 doesn't mean that I got to cube it before I take the square root. I can flip the order, it's okay. If I take the square root of 9, what's square root of 9? 3. And 3 cubed becomes a lot easier, right? 3 cubed is 27, right? It's a lot more manageable than trying to figure out what 9 cubed is. That's a big number. And then to try to figure out the square root, that'll take a lot longer than just forcing that number smaller and then raising it to a higher power. Right, so this ends up being 18 plus 6 minus 16/3 minus 4, which is 44/3. But you don't have to go this far on the test without a calculator. If you leave it in this numeric form, that's fine. Okay, number 10, evaluate integral of tangent squared, secant squared. Now, if you look at this and you feel like, okay, maybe I can just adapt my rule here. I have a rule for secant tangent, so why not just square it and then just make the integral of this turn to the secant squared? Remember, these are very restrictive rules here. If I don't have a perfect match with the rule in front of me, I don't have a rule to use. I can't just square this and make the antiderivative this squared equal to this squared, right? It doesn't, it's not as flexible as you would like. So we have to recognize there's no rule that we can use, even though it looks like it's similar. So we know we got to go through U substitution. And U substitution is asking what could be the U value. We don't see parentheses, but we can create some parentheses, right? We know these exponents are written in shorthand form here. So now that you have two sets of parentheses, at least only one can be the U value, but at least you have some options to choose from, right? Either you're choosing secant or you're choosing tangent. But if you choose secant, secant is not as good of a fit because the derivative of secant is secant tangent. So I would need something that is secant tangent waiting for me to cancel out. I don't have a secant tangent waiting for me. I have a tangent squared. That's not a perfect fit there. But what if the U value was tangent? If the U value is tangent, the derivative will be secant squared, and secant squared, we have a match with the derivative that we can look forward or that we can look ahead and see things will cancel out for us. Okay, so that's how we decide. It takes a little bit of trial and error sometimes to figure out the U value. Cross multiply. Make your substitutions. Secant cancels out. U squared becomes U cubed over 3. Okay, we're not quite ready to plug in. Now on my key, I converted the bounds, converted the x to be u's. But another option that you can do is you can get the u to come back in terms of x. I'm going to pull the 1/3 out and replace the u in terms of tangent. And then once your antiderivative is in terms of x, you can work the bounds in, right? Because the bounds are in terms of x. We need our antiderivative in terms of x as well. Either your variable are matching in terms of x, or your variable is matching in terms of u. But we can't leave this as u and plug in x. Okay, upper bound first. So 1/3 tangent pi over 3 cubed minus 1/3 tangent of 0 cubed. Okay, I do want to point something out again, just like yesterday, I mentioned this. This is not far enough. Okay, if there's trig involved, it's not like this where you can leave your answer unsimplified. Right? You have to get the trig resolved. Now, after this step, if you still have fractions left over, you can leave those fractions alone. But tangent of pi over 3, tangent of 0 is not far enough. We got to use unit circle knowledge to go one step further. So tangent of pi over 3, we know that order pair is 1/2 comma root 3 over 2. And it's sine over cosine or y over x. So it's going to be root 3 over 1, which is just root 3. So 1/3 times root 3 cubed minus 1/3 times 0 cubed, which reduces to be root 3. But if you want to leave your answer in this form, now this is okay. Okay, you can leave your answer unsimplified once it's down to a numeric value, but you cannot leave your answer unsimplified if there is a trig still remaining in your answer. Okay, so look on the board there. Those are the topics that you're going to be expected to see, that you're going to expect to see on the test. So let me just read from top to bottom there. So first, make sure you memorize your trig interval rules, just like how you did on the quiz. Power rule, you'll see a power rule problem, similar to what you saw on the quiz. U substitution, depth integrals, which just really what we did with number 9, these types of problems. And number 10, where you have to take the antiderivative and then plug in the upper and lower bound. Depth integrals involving trig, a problem like number 10. U substitution, change your variable. We saw that on the previous page where the x's didn't quite go away after your initial process of U substitution. You have to rearrange your U value, solve in terms of x, then plug in, clean that up, and then do power rule. So change your variable. Second theorem, we saw that yesterday. We'll see that again today. Average value theorem, we saw that yesterday. We'll see that again today. Even and odd functions, okay. Absolute value integrals, and then particle motion, PVA. Similar to the quiz. Remember how in the quiz you got from f double prime to f of x, and you took your antiderivative along the way, and plus c shows up. Same thing. It's just instead of f prime, f double prime, it's position, velocity, acceleration. That's the same process. Acceleration is antiderivative, brings you to velocity. Velocity is antiderivative, brings you to position. Along the way, plus c shows up. So it's the exact same process as on your quiz, just with these variables instead of particle motion variables instead of f of x, f prime, f double prime. Okay. So these PVA motion problems that you see on page 5 and page 7, these are going to be more of what we're going to be expected to see on the FRQ portion of your test. So we'll come back to these. These won't be on the test, won't be on Friday's test. We have to come back to this and review this for next Fridays. But page 5 and 7, no need to worry about that. So let's go to page 9. All right, so given our function, find the average value in the interval. So we have to build our average value theorem and then put into our formula. Okay. Make sure we memorize this formula here. So it's really just area divided by the width equals the height. So we're just trying to find the height, the average height along my graph here. Okay, so first things first, replace all the A's and B's with 1 and 3, replace the function with the problem that we're working on. So when I see a problem like this, I prefer to work from right to left. The 1/2 is going to be pretty much the last thing that I do. I know the bounds is also near what I want to do at the end. So the 1/2 and 1/3, 1 and 3, I'm not going to involve that. I'm going to focus on taking the antiderivative, and then I can plug in my upper and lower bound, and then I'll work in that 1/2. Okay. But if you want to multiply that 1/2 through now, you can. It's algebraically, that's fine. You can do that if you like. So if you want to do that, our numbers will look a little different, but in the end, our answers will match up. So if I just want to focus on taking the in-depth integral here, what process do you think we're going to use? What's our strategy for this problem? Is it use substitution or is it something else? Does the denominator give you an idea how to categorize this? What do you notice about the denominator? There's only what? Only one term, right? It's not x squared plus 1, or it's not like 4 minus x squared. If there's only one term there, this looks like number 1 that we just talked about, right? If there's only one term there, 5 root x is considered one term, and so is x squared. So we can split this up. There's no need for power rule, even though you may be looking at that parentheses thinking that is use substitution, but we need to recognize, okay, this is not, there's no need for us to go through use substitution. And then if we try to go through substitution, we're not going to be able to find something that's going to fit that process. So I'll distribute that 4 through, and I'm going to start separating into individual fractions. The x squared cancels out. 4 over x squared is not ready for power rule, so we want to bring that to the top. Okay, so now we have a much cleaner problem to work with. 4 becomes 4x. 4x to the -2 becomes 4x to the -1 over -1. So we're just applying power rule for these terms separately. I do want to plug in the bounds, but I'm just going to do a little bit of cleanup before I plug in the bounds here. So I'll make this 4x minus 4 over x. So I've done the calculus with power rule. Now I'm ready to involve the bounds. So plug in the 1 and the 3. Minus big parentheses. And then the lower bound as well, 4 minus 4. The 4's canceled out. That's nice. So we have 12 minus 4/3. So this is my area component. So I want to kind of show what we've gathered so far. This is not quite the answer. This is representing this portion of our problem, right? 12 minus 4/3. If you want to leave it in this form, it's fine without a calculator. Or you could go 36 over 3 minus 4/3 and make it 32 over 3. But this is fine. But either way, either this or this, we have to still multiply by 1/2. We have the area, but we still have to involve the width to get to the height. So our average value is 16/3. It's the area and the width to get to the height. Part B says find the C value. So C value just means, okay, I have the Y value. Now let's look for the X. So we're just taking that 16/3, putting it into the Y, and then solve for X. So we're just using the function, trying to work backwards and solve for X. That just basically means the X value solution. Replace the Y with 16/3. I'm just going to cross multiply and find a way to solve for X. After I cross multiplied, I distributed the 12 through. I added like terms, divided by 4, take the square root, plus or minus root 3. But are both of these valid C values? Where do we need the C value to live? Between, right? Between the interval. So the only C value we can keep is what? Root 3, right? Since negative root 3 is outside of our range. Okay. Number 2. We're asked to find the derivative of this function. If I want to find the derivative of this function, I'm basically putting two opposing operations on top of one another. And this is applying second theorem of calculus. So this is formula we need to make sure we memorize as well. And second theorem says, if I'm pairing derivative and integrals on top of the same function, we're going to skip a lot of things. We're going to skip all the integral stop process. We're going to skip all the derivative process because we know that we're going someplace and we're coming right back. So this function is not going to go anywhere, but the upper bound variable is going to remain. It's going to have an impact on the answer, and we're just skipping to the end. So the end is the upper bound will end up inside the function, and then the derivative of the upper bound variable is also going to stay in my answer. All right. So I want us to recognize this is a shortcut process. If we want to do this in full, we would get this ready. We'll do power rule, plug in upper and lower bound, get all that cleaned up, and then take the derivative. And so that would take, 3, 4, 5 lines. Meanwhile, this process will just jump from, we're just skipping all that step and going to the very end. So if I want to set this up, though, if I want to find the derivative of this function, I'm just trying to line it up so that it matches the rule that I want to follow. What do you notice that is a little bit off about my problem versus the rule that I want to use? Anything about the bounds that look a little different than the rule? What would I prefer my lower bound to be? What does the A represent? Constant. And then the upper bound is the variable here. So I would like to have the bounds in to be matching my rule. So I can flip the bounds, but if I flip the bounds, what adjustment do we have to make? We can't just flip the bounds without doing anything, right? Because then we're changing the problem. How can we flip the bounds and still work on the same problem? Make it negative, yeah. Okay, so now everything is lined up. We can now follow the rule. The rule says f of p of x, which means take the upper bound, insert it into the variable of the function. So take the 3x to the fourth, plug into everywhere you see the t. Times the upper bound's derivative, 3x to the fourth becomes 12x cubed. So we would much prefer going through this much faster method than having to get this ready for power rule, bring that root t up, get it ready for power rule, plug in the upper and lower bound, clean that up, and then take the derivative, right? That would take a lot longer. So here in my cleanup, I'll get 12 and 2 to cancel out to be 6. 6 times negative 5 is negative 30. Technically, we can clean this up a little bit more because we know that square root of x to the fourth is just x squared. But unsimplified is fine. Okay, your homework is to finish page 9. So tomorrow, we're going to do a full test review on page 13 and 14. And then Thursday, we need to transition over to working on the calculator portion. So I'm only going to have tomorrow left in class to do a full review. But if you look on the board there, I have health sessions coming up. So tomorrow morning, I can go over additional problems that you guys have. Thursday morning, I do have a meeting at 7:45. So coming at 7:15 to 7:40, well, we can work through some problems. And then on Friday, we'll do the morning review for your test. I can make the phones.